it allows me to record lessons. I am now recording everything that you see and hear, at least on my laptop. Okay, and those will be posted on YouTube. I'm getting a little bit of a slow start to that, but usually I'll have them up the day that I record them. Okay, so first part is notation. The first type of notation is inequality notation. This is something you should have seen before. I might have x is greater than -3 and less than or equal to +5. Okay? What's the difference between less than and less than or equal to? Does this include -3? No, it excludes -3. Okay? So this is exclusive. Okay? Does it include 5, class? Yes, so this is inclusive. Simple as that. So that's inequality notation. Next is set notation. And in set notation, when I talk about a set, and this is something we will revisit later on with sets, but sets, when I say a set, I mean like a collection. Like you have a set of silverware, it's a collection of silverware. If I say the set is all people in this room, that would include all of you, Mrs. Hendry, and myself, right? We'd all be in a set, okay? If I ask a set of all the textbooks here, it would be all the textbook numbers, right? Well, I can also have set notation for x, and that would be the set of those curly brackets, say the set of all x such that. You see how this is a language? This is math language. The set of all x such that -3 is less than x is less than or equal to 5. This says the same thing as this, except it's in set notation. Okay? Just a different notation. And then the last is interval. Last is interval notation. And with interval notation, I need to have something that says I'm excluding -3. I want to have -3 to 5 be my interval, but I need something to show me that I'm excluding -3. I want to have some kind of symbol there, parentheses, bracket. Yes, sir? What do I use? Do you know? Parentheses. That's right. A parentheses means I'm excluding -3 from the interval. And 5 needs to be included. So what do I use? Someone raise your hand, please. Devin? A bracket, right? Square bracket. So we have exclusive is parentheses, inclusive is the square bracket. Is that clear to everybody? So we have inequality, set notation, and interval notation. Can you see, sir? Okay. All right. Any questions on that? No? Okay. All right. So that's that. Now moving forward, we can start our lesson. And you can see in your book, right, it has kind of a more symbolic understanding of all those notations right there. So we go forward to the bottom of page 5, and we start working on some examples. You see both of these, the one on the left and the right, are both finite intervals. Okay? So our finite intervals we want to represent with inequality, set notation, and interval notation. So we'll start with an inequality. Now, the inequality, first off, where does the interval start, class? Okay, someone raise your hand. Where does the interval start? Yes, Ethan. -3, right? So we know we're going to start at -3. Now, does it include -3, Ethan? How do you know?
Because that's the starting point.
It's the starting point, but what? Yes, ma'am? It's filled in, yes. Okay, so it's a solid circle. It's not open, it's closed, right? So 3, or -3, is less than or equal to, because it's inclusive, x, which is, again, less than or equal to what, class? 2, because that's where the interval ends. You see how we do that? Okay. Now set notation, once you have inequality, set notation is very simple because it's the exact same thing except for you put the set of all x such that, and then write the inequality. Negative 3 is less than or equal to x is less than or equal to 2. Just like that. And then for interval notation, we know that our interval is negative 3 to positive 2. Do I include negative 3 and positive 2, class? Yes. So what do I use? Parentheses or square brackets, class? Square brackets. Very good. Okay, so I use my brackets there. Negative 3 to positive 2. That's my interval notation. Next, I'll do the one on the right here. Who can tell me by raising your hand what is different from this interval and this interval? What's the difference? Isaiah.
On the second interval, it has a closed circle or an open circle for the beginning of it.
For negative 3, right? So what does that mean about negative 3 in the
That
interval?
means that it's not included.
It's excluded. Very good. So negative 3 is excluded, so we know it's negative 3 is less than, not less than or equal to, x, but 2 is the same. Right? So we move forward with set notation, the set of all x such that negative 3 is less than x is less than or equal to 2. Okay? And now who can tell me, negative 3 is excluded, so who can tell me what I use, parentheses or brackets? Someone raise your hand, please. Yes. Yes. I forgot your first name for just Tyler. Okay. I know your last name, but I should have just called Sayverier, and that would have just worked. Yes, good. Thank you, Tyler. So Tyler said I use parentheses, and why, Tyler? Very good. And 2 gets a bracket. Very good, sir. Any questions on this? Pretty clear, huh? Okay, nice. Now, you guys can see why having your book is key, right? You're just filling in instead of drawing all the stuff, right? Now, for those of you that might be stressing out about not having your book here today, the fact is that I do record these lessons and put them on YouTube, so you don't need to freak out. You can always spend the time. Obviously, you don't want to go and spend the time and write it in the book and watch the lesson after school, but you're not going to miss out on anything because you're missing your book. It just means you have to do extra work. Is that clear? Okay. All right. So next, before we had a finite interval. Our next example, we have an infinite interval. Okay? So for this one, we have an inequality. We're going to start with inequality. Now, do I have a starting point of my interval, class? No. So I don't have to be concerned with my inequality with where it starts because there's no starting point. But I know that I've got an ending point. And what does that mean? X is going to be less than or greater than? Less than what, class? 2. And it's going to be less than or less than and equal to? Less than or equal to 2. Okay? So that's my inequality. Again, once I have inequality, it's easy to do set notation. Set of all x such that x is less than or equal to 2. Now my interval notation is a little bit different in the sense that because I have to have something designating where my interval starts, I can't just ignore it. So what should I use to designate the beginning? Yes, Leslie? Yes, but you're missing...
Negative.
Yes, negative infinity. And class, do you think it should be inclusive or exclusive for negative infinity? Exclusive. And I think this is just a great example of where math kind of mirrors our understanding of God. We have this interval that we can understand and describe, but it can never quite reach infinity, so it doesn't include infinity. So infinity is set apart from the rest of these numbers. In the sense, it's like God is holy and completely different in his being than us, right? When we talk about our infinite God, it's beyond our understanding and it's beyond our capacity to ever reach, to ever be infinite. We are finite creations, and he is infinite. It's beautiful. So negative infinity exclusive to 2 inclusive. Clear? Now here, do I have a beginning, class?
Yes.
Yes, on the right. Do I have an end?
No.
No. Okay. 2 is exclusive, so it's x is greater than 2. Right? Greater than 2. Once again, we go to our set notation. The set of all x such that. The set of all x such that x is greater than 2. And now, for our interval notation, am I including 2, class? No. So 2 is excluded. And then what's my endpoint, class? What's the second part? Infinity. And in your book, it uses positive infinity. And it's exclusive. It puts a positive sign out there. I won't ever take off points if you don't include the positive, but I will if you don't include the negative. Okay? So, any questions about that? Okay. All right. So moving forward, there's a bunch of good questions here that you can use to study. Class, there are things that I skip in the book, but it doesn't mean they're worthless. It also, if I skip something in the book, man, that's probably a pretty good thing to ask on a test, right? Because if it's in the book, it means it's like right there with the material, but, it'd probably be a good question for a test. Not exactly the same, obviously, but if you're studying, just because I skipped something doesn't mean that you shouldn't look at it. So I'll give you an example. I'm not going to do this on the book, but what do the intervals this first, second, and third have in common? And what's the difference? I'll ask that question. What's the difference between this first interval and the last interval? Someone raise your hand. Yes, sir, Brian.
The first one is totally inclusive. The second is totally exclusive.
Right. So what numbers did this first and the second have in common? What do they have in common?
All positives.
Yeah, but what numbers exactly? They have the same start and end points, yeah. But I would say they all have 1, 2, 3, and 4, right? And potentially decimals in between there as well, right? But they don't have 0 and 5 in common. Does that make sense? Okay. So that's a good kind of thing to think about and to think about what's going on there. All right, so moving forward, we now need to do a little bit more bookkeeping. Okay, so if I tell you that we're going to do end behavior, as long as a function has end behavior, which means what does the function do at the ends, then you will write this. As x goes to positive infinity, f of x goes to what? That's the question. And as x goes to negative infinity, f of x goes to what? So this notation, this way of answering the question, if I ask end behavior on a test, bam, you write that, and you've already got some points because you have the correct format for your answer. Okay? But with that being said, the only thing that you have to answer is what is my function doing? What goes right there? So as long as a function has end behavior, which it may or may not have end behavior, and I will answer that implied question in a second, you're going to write this form, right? So immediately your brain should just think, damn, do that form, and it makes it easier to answer the question. Okay? So that's the format right there, and you'll see that in your book. So right here we have a function. This is what I use for the bell ringer. Okay? It's asking the domain. Well, the domain goes from negative infinity to positive infinity. It never stops, right? You see that? The domain, no matter where. Okay. And then it camouflaged itself. I mean, it's all good. Okay, so no matter where I put my pen, you can't see it on this graph, but you can see that eventually, if I went up high enough, it would intersect all the way this way to negative infinity, all the way this way to positive infinity. So the domain is negative infinity to positive infinity, and we see that in inequality set and interval notation. And then the range we went over is from 0 to positive infinity. So that's y is greater than or equal to 0 because it includes 0. And then we can see that right here in interval notation as well. But what I'd like to draw our attention to is the end behavior. So the end behavior is asking me and asking us, what does the function do at its ends? Okay? So the first thing is, as x goes to positive infinity, that means as I'm going to the right, what is my function doing? Who can tell me? As I go to the right, what is my function doing? Class, what is it doing? It's increasing, right? Does it have a bound? Does it ever stop increasing? No. So as x goes to the right, my function f of x is going to positive infinity. Okay? So that's what you see right there. And as x goes to the left, as I'm going to the left, my function is doing what? It's increasing all the way up to positive, what class? Infinity. You see? So that's our end behavior. Then if we go to this question, our next example, I'm just going to do the domain and range in interval notation. Okay, for these, I'm not going to go through all of them because I think we've got that already. The domain, can I go all the way to the left? Yeah? Does my function go all the way to the left? Is there ever any point? No, so that's negative infinity to positive infinity. So that's my interval notation right there. Or that's my domain. Negative infinity to positive infinity, exclusive on both of them. Now, my range is a little bit different. Obviously, it doesn't exist here. But look at this function. What is it doing? It's getting closer and closer to what, class? 0, the x-axis, 0. But does it ever touch it, class? No, it doesn't ever touch. What is that called? Raise your hand, someone who can tell me. What is that called when function gets closer and closer to a value? Yes, an asymptote. A-S-Y-M-P-T-O-T-E. Asymptote. Okay, it's a good word. Like it. So it's an asymptote at y equals 0. Very good. So the range starts at 0, but does it include 0, class? No, it's exclusive 0 all the way to positive infinity. So if we do it in interval notation, that's 0 to positive infinity. Okay. And then scrolling down a little bit here, we have our end behavior. Okay, so as x goes to positive infinity, as I'm going to the right, what is my function doing, class? Increasing, right? So what does that mean? Someone raise your hand. What is my function doing? My function is going to what? Someone raise the hand. Raise the hand. Yes, Doug? Positive infinity. Good job. So as x goes to positive infinity, my function f of x also goes to positive infinity. That's pretty clear. Now, as I'm going to the left, what is my function doing? What is my function doing? Yes?
Negative infinity.
My function isn't going to negative infinity because if my function was going to negative infinity, it would mean it's going all the way down. It's not going to positive infinity. Think, what is my function getting closer and closer to as it goes to the end? 0. Is that clear? It's getting closer and closer to 0. Sometimes the way I think about it is it's like if there was a little person on the function and I was just walking in this direction to the left, where am I getting closer and closer to? Closer and closer to 0, right? I'm not going all the way down to negative infinity. I'm going closer and closer to 0. Does that make sense? Okay. So the function is going to 0. Clear? All right. Any questions on that? Okay. So there was an implied question. I don't want to leave you hanging on that. What is an example of a function that does not have end behavior? Well, I will give you an example of a function that has no end behavior. If I were to draw a function that looked like this, just want to use a different color, that looks like this. Someone tell me, raise your hand, why this function doesn't have end behavior. Yes, sir?
It doesn't go to infinity.
Yeah, it doesn't go to infinity. It doesn't. If I'm asking as x goes to infinity, what's my function doing? The function's not doing anything. It doesn't even exist there. nor does it exist at negative infinity. Sometimes you might have something where you have something like this where it has end behavior in one direction and not the other. But you guys understand the idea of end behavior? Any questions on that? No? Good? Yes, sir.
So, would there still be a behavior to the main?
Yes, on this one it would have end behavior.
It would just be one.
Exactly. You would say, as x goes to positive infinity, my function goes to positive infinity. You see? But it wouldn't have end behavior on the other side. Okay? Is that clear? Okay. Any questions? No? Okay. Moving forward. Graphing a linear function on a restricted domain. Okay. So we all know how to graph a linear function. Okay? But we've got to figure out how to graph a linear function on a restricted domain. Sorry about this, guys. Okay. So if we have, first off, the domain of this function, what is it? I'll answer that. -4 to +4. Is that an infinite domain? No. It's a domain that's restricted. So that's what a restricted domain means. So that's what we're going to work on. If we look at this function here, number 9, our function is -1/2 x plus 2. Its domain is from -6 inclusive to +2 exclusive. Now, when we want to graph a linear function or any function, generally speaking, we want to create an f of x chart. Okay? What would be a wise choice for the first number that I pick for x? Someone raise your hand. 1. Not quite what I'm looking for.
2.
Yes.
0.
Not 0. No. What's it?
2.
2 would be a good choice for my final point, my end point, but what would be my first point? -6. Why should I choose -6?
Because it's the starting point.
Yeah, it's the starting point. It's the beginning of the domain. So I should choose -6 and +2, and then someone shout out a number that I can use. Another number I can use. Anyone? -6, +2, what's another number?
-4.
Yeah, I can use -4. That works. I'm going to use 0 just because I feel like it. No, you know what? I'll honor your courage. I'll use -4. You're welcome. So, look, could I use -10, class? No. Could I use 50, class? No. Why? Because it's outside the
Restricted domain.
It's outside of the domain. Yes, outside the domain of this function. Good. Okay, so -6. When I want to find out the value of a function at a given value of x, what do? I plug it in. Very good. I plug it in. So I'm plugging in -6 to this function here. I do -1/2. I'm going to do the arithmetic fairly quickly because something you know. Negative times a negative is positive. 1/2 of 6 is 3. Plus 2 is 5. -1/2 of -4 plus 2 equals, remember I'm plugging into this function. Negative times negative is positive. 1/2 of 4 is 2. 2 plus 2 equals 4. -1/2 of 2 plus 2 equals -2. 1/2 of that is -1 plus 2 equals 1. Okay, now -6, 5. Is that going to be an open or closed point, class? Closed. Why, class? Because it's inclusive. Very good. -4, 4. And 2, 1. Now, is 2, 1 inclusive or exclusive, class? Exclusive. So I'm going to draw an open point. There you go. Connect them with a line, and I've graphed a function on the restricted domain. You see that? Any questions about that there? Yes, sir.
Why is 2 exclusive again?
Tell me.
Oh, because it's, yeah, I see what it
You see?
is. Yeah,
Because it's less than.
Yeah.
Exactly. Very good. Thank you, sir. All right, any questions? All right. Okay, so moving forward, this is the last thing we're presenting in the lesson, modeling with a linear function. So just about anything can be modeled with a mathematical function, whether it's the rate that the air conditioning gets pumped into a building or the rate that water starts to boil or anything like that based on the temperature that it's on. Whatever it may be, there's lots of things. You know, the rate at the amount of the higher your grade gets because of your grade is a function of the study time or amount of time you sleep in a night. There's all sorts of things that we can model with functions. Here's an example of something that we can model with a linear function. Joyce jogs at a rate of 1 mile every 10 minutes for a total of 40 minutes. So she jogs 1 mile every 10 minutes. How far does she jog after 40 minutes? How far is she going? 4 miles, right? And so you see here she's jogging 1 mile every 10 minutes. At the end of 40 minutes, she's gone 4 miles. And this is modeling with a linear function. Okay? So what we're going to do is an example for ourselves. A candle 6 inches high burns at a rate of 1 inch every 2 hours for 5 hours. Okay, so if it burns at a rate of 1 inch every 2 hours, the candle's burning rate is how many inches per hour? 1/2. Thank you, sir. 1/2 inch per hour. Okay. The candle's height, h, in inches at any time t in hours is modeled by h of t equals what? Now we know it's a linear function, so our form is going to be y equals mx plus b, right, class? So instead of y, we have h of t, and instead of m, what is m? Who could tell me what m is in this situation? Slope, right? What's another word for slope, class? Begins with an R? Rate of change, right? So what's the rate of change in our situation, class? 1/2. Now, is the candle getting taller or shorter? It's decreasing, so it's negative. Okay, so it's negative 1/2, but it's h of t, not f of x, right? T is my independent variable, right? So it's negative 1/2 of what? What goes next? Not x, but t. Does that make sense? Class, our variable is t. It's time. X, it wouldn't make sense if I put x here because x means nothing in the context of our function, right? I don't know what x is, but I know t is time. T in hours here. We see that here. Time is a little bit confusing because it says time h here, but t is the variable. T is the variable and h. Okay? Now, b is what we usually call our y-intercept, but really b is the value of our dependent variable, which in this case is height, when our independent variable, which in this case is time, is equal to 0. So b is the y-intercept, or the value of h when t is equal to 0. So t equals 0 means the time is what? 0. Hasn't started burning yet. So what's the height of the candle before it started burning? 6 inches. So what's b in this case, class? 6, and we've got our function. Okay. Next question, it says, since the candle burns for 5 hours, the domain is restricted to the interval 0 to what, class? 5. Okay. The domain is the allowable values for my independent variable. Usually this is x, but in this case it's t, right? So t goes from 0 to 5. So my domain is 0 to 5. Okay, now I'm going to go ahead and plot my function. Starts here at 6. Then it goes down 1/2 every hour. So it goes down 1/2, 1/2, 1/2, 1/2, until I get to 5. Does it include my value here at 5? Yeah, it does. Then I go ahead and take, whoops. And I plotted it. Good. Now, the range is the values of the dependent variable. In this case, the dependent variable is height. So it goes from the lowest value to the highest value. First off, what's the highest value? What's the highest height of the candle at any point? 6, right? And it's inclusive. Okay. And what's the smallest height, class? 3.5. We didn't have to plot that to figure that out. We could have just plugged in 5 for t, and we would have gotten that our height is 3.5 at 5 hours. So we didn't have to plot it, but it just makes it easier to see. And so that's our range. Is that clear? Any questions about that? That's modeling with a linear function. You model the situation with a linear function. Now, any questions? I know that was a lot. You guys did very well, okay? We have homework. You're going to have some time. Obviously, the first period of the day is a little bit less time because we have announcements and things like that. But you have about 8 minutes to start on your homework. Your homework is on page 9. It's page 12. Starts on page 12. It's numbers 1 through 12. Okay? So it ends here. Ends here on number 12. Now, before you guys go into your own world, first off, remember it's independent work. Second off, the way that this works is this. Your homework is graded in two regards, completion and accuracy. Completion means you've completed all your work. You can get up to 5 points on that. Okay? Bell ringers are worth 2 points, by the way. So completion is 5 points, and then accuracy is 3 points. What's the accuracy? How's that graded? There's a MyCCA assessment that once you're done with your homework, you go on MyCCA, obviously before class starts, so really the night before, or whenever you finish your homework. You go on MyCCA and you'll say, what's the answer to number 7 or 9 or 3 or whatever it is, and it'll be multiple choice. So it's not like, oh, I have to make sure I type in the right thing. No, it's A, B, or C. Usually it's only 3 answers. And you just choose whatever the answer is, okay? Whatever the correct answer is. Obviously, you have to do your homework before you go on MyCCA. A lot of times it'll be time limited, so you're not going to be able to just open it up and then, you understand what I'm saying? So you do your homework, then you go on MyCCA, you complete the assessment for the homework, okay? Now, last thing. What did you guys do before you came to class today? You did something. You watched the videos. What do you guys think you have to do today before class tomorrow? Yeah, so you've got to do your homework, which is what we just did. And then you go to lesson 1.2, math on the spot videos. There are only 2 this time. Okay, concept 2 and 3. For the record, did those videos help? For those of you that are watching, which is hopefully all of you, the videos helped, right? Okay. All right, so hopefully they continue to help you guys. I always appreciate feedback, so you let me know if I make any kind of mistakes. Any questions? Yes, sir.
The homework pages for my book are ripped out.
The homework pages for your book are ripped out. I'm sorry. There are some, remember when I said that they're being used? If that is true for anybody in this room, you can either print out the homework pages, and that will be sufficient. You can just go online to the online textbook and print those out. Or if you want, you can just let me know, just send an email, and I can print them out today if that's any kind of a thing for you. In fact, what I will do is I'm going to go ahead and print out some copies of the homework, and if anybody in this class just wants to come to my room either during lunch or after school, you can come and pick up the homework if it's missing from your book. Clear? Thank you for letting me know, sir. Any other questions? Yeah. And also, guys, my helps classes are today after school. Yes, woohoo, helps class. I'm generally here every day for at least a little while, but today specifically my helps class. I'm in 34003B, which is Mrs. Muller's room, if you're aware of her. It's just a few rooms down, literally 4 rooms down. Yeah, 4 rooms down the hall. Any other questions? Okay, thank you guys for your good work today. You have, looks like 4 minutes to do your homework. Obviously, we want to do it individually, but if you have any questions, go ahead and raise your hands.